Welcome to our lecture where we are going to review how to choose the appropriate statistical test, which is the final section that gets included in the methods when putting together a paper. So the tests we're going to look at are going to be specific to only continuous data. So essentially looking at numeric data on running on a scale there. It's not going to be specific to data where you assign outcomes to a specific group. So the first test we're going to talk about is a one sample t-test, and this is used when you have only one group, and you're going to compare that the mean for that group for some dependent variable to a known value. So this could be a norm value that's been previously established. It could be comparing it to published results from a similar previous study, or it could be comparing it to a predefined performance standard. So an example research question that would require a one sample t-test is the average VO2 max of the women's soccer team different from the published collegiate female norm of 42 milliliters per kilogram per minute. Okay, so the one group is just going to be the women's soccer team, and we're comparing the mean value of their VO2 max to a previously known value of 42 milliliters per kilogram per minute. When we analyze statistical tests, there's going to be a p-value that's reported. And essentially, if the p-value is less than 0.05, this means that there is a difference between the values. Okay, so we would say if the p is less than 0.05, there is a statistical difference. So in this case, it would mean that the group mean is different from that known value we're comparing it to. For each of these tests that we go through, I'm going to show you just how this example of data, and you can see kind of visualize how that data is distributed to get an understanding of where there is a difference. So for all these graphs, any of the individual dots, those are going to represent one participant, so their value. And then the red square is going to be the entire group's average. And then those lines extending from it are, this is the 95% range that we expect the average to be within. And so on the left side here, we're comparing this group mean to our reference value of 42, and we can see that that group mean is higher than that, so there would be a significant difference. Here we'd get a p-value less than 0.05. This example on the right, you can see that there's about half the participants have a VO2 higher than 42, the other half of a VO2 lower than 42, and so that average and that kind of confidence interval of the average crosses over that known value. So this would result in a p-value greater than 0.05, saying there's not a significant difference. Our next test is a two sample t-test, and this is used when we have two separate groups. So it can be for comparing men to women, injured athletes to uninjured athletes, comparing a treatment group to a control group. And for this, we're looking at the mean from the first group and comparing it to the mean from the second group. An example research question would be, do athletes recovering from ACL reconstruction surgery have less knee extensor strength than uninjured athletes? So our two groups, we have the ACL reconstruction group and we have the uninjured group. And we're going to compare the mean of their knee extensor strength. For the interpretation, if we get a p-value less than 0.05, this means that the group means are significantly different from each other. Okay, so our figure on the left here, this shows the ACL reconstruction group first, and then our control or our healthy group. Here we're looking for, do those means overlap each other? And we can see that on the left here, we get a p-value less than 0.05 because the ACLR, that reconstruction group, the average knee extensor strength is lower than that control group, resulting in a significant difference. An example on the right, though, shows that there's overlap between these mean values, and so this indicates that there's no significant difference. And you would have a p-value of greater than 0.05. Our next test is a paired t-test. So this is when we have one group, but each participant is going to be tested under two conditions. So it could be a pre versus post test. It could be doing intervention 1 compared to intervention 2, but each participant is doing both those interventions at separate times. And here you're going to compare the mean difference between the two conditions. So essentially, we want the mean difference to be 0, or that would mean that the scores were identical. And so if the mean difference is not 0, this means that they are significantly different. So an example research question would be, is sprint time different when athletes perform a dynamic warm-up versus a passive warm-up? Okay, so the one group is just going to be the athletes. The two conditions is they're going to do a dynamic warm-up and then sprint, and then they're going to do a passive warm-up and then sprint, or vice versa order. And there we're going to look at the sprint time, after their dynamic warm-up and their sprint time after their passive warm-up, and see if the mean value is different than 0. If that p-value is less than 0.05, this means that the mean difference between the two measures is significant and that it's greater than or less than 0. So here we've got on the left, so this dashed line horizontally, this is going to be that mean difference of 0. And so if the mean of the group crosses over that 0, this means that there's no significant difference. Here, since we see that the mean value is less than 0, there is a significant difference and we'd have a p-value less than 0.05. The graph on the right, we see that mean value is overlapping 0, and so this would indicate that there is no significant difference, okay? About half the participants did better with the dynamic stretching, about half did better with the passive stretching. So we get a p-value greater than 0.05 for that one. Our next test is a one-way ANOVA, and this is used when we have 3 or more separate groups. So it could be having a training program with Group A, Group B, and Group C, which are each different training programs. And here you're comparing the means for all the groups against each other. The example research question is there a difference in vertical jump height improvement between athletes completing plyometric, resistance, or combined training? So we've got our 3 different groups. We have the plyometric group, the resistance group, and the combined group. And then we're going to compare the mean of their change in jump height after these training programs. So if we get a p-value of less than 0.05 with the ANOVA test, this just tells us at least one group mean is different than the other group mean. It doesn't tell us which ones are different. In order to find that out, we have to do pairwise comparisons, which essentially will do multiple 2-sample t-tests to see which groups are actually different from each other. Okay, so on the left here, we've got our 3 groups. We've got our plyometric group, resistance group, and combined group. We would get a significant ANOVA p-value here of less than 0.05, and then we'd have to do pairwise comparisons, which would indicate the plyometric group had greater improvements than the resistance group. But we see overlap between the resistance and combined, so those aren't different. And we see an overlap between the plyometric and combined, so those also aren't different. Okay, so with ANOVA, you can have one difference. We could also have it where plyometric is different than resistance, plyometric is different than combined, and resistance is different than combined. But we don't see that in this case because there is some overlap among those groups. On the right, this ANOVA would result in a p-value of greater than 0.05. And here we don't have to do any pairwise comparisons. It just tells us that there's no significant difference because all those means are going to overlap. Next, we have a repeated measures ANOVA, and this is used when we have one group, but they're going to be measured at 3 different time points or under 3 different conditions. And so it could be a pre, mid, or post-training collections. And what you do is you compare the mean for all those group collections amongst themselves. So the example research question could be, is there a difference in mean heart rate across 3 different stages of a graded exercise test? Rest, moderate intensity, and high intensity. Okay, so we just have one group, one sample size of participants completing an exercise test. The outcome variable would be the heart rate, and we would measure the heart rate at rest during the moderate intensity portion and then during the high intensity portion of the graded exercise test. Similar to that ANOVA, again, p-value less than 0.05 says that at least one of the measurement means is different than another measurement mean, and then we would need to perform these pairwise comparisons or these paired t-tests to determine which measurements are actually different. Okay, so on the left here, we get a repeated measures ANOVA with a p-value less than 0.05, and then the pairwise comparison shows that the rest heart rate was lower than the moderate intensity portion, and the rest heart rate was lower than the high intensity portion, but we don't see a difference between heart rates between the moderate and the high. On the right, we have a non-significant, so a p-value of 0.05, and here you see those means are all overlapping, so there's no significant difference in heart rate depending on the timing it was collected. The last test we're going to discuss is a correlation analysis, and this is used when you have one sample again, and you're going to be comparing 2 continuous variables. So you have these 2 dependent variables that you're looking at. How are they related? So it tells us how strong the relationship is and the direction of that relationship. So an example is there a relationship between weekly training volume, the number of hours per week, and VO2 max in collegiate runners? Now, when we interpret correlations, it can be a little bit different than these other tests. First, we can tell is the correlation. So it's going to range in a value from -1 up to +1. If it results in a positive correlation, this means that as one variable increases, the other variable also increases. Whereas the negative correlation means as one variable increases, the other variable is going to decrease. We can also quantify the strength of the relationship. So essentially, if it ranges from -1 to positive, or sorry, from negative 0.1 to positive 0.1, this means it's negligible. They're not really related to each other. If we have 0.1 to 0.29 or negative 0.1 to negative 0.29, there's a small relationship between them. If there's a correlation of 0.3 to 0.49 or negative 0.3 to negative 0.49, this is a medium correlation. And then anything 0.5 larger or negative 0.5 to negative 0.1 would be considered a large relationship. So when I talk about these relationships, we essentially put together these scatter plots. On the x-axis, we have the weekly training value. On the y-axis, we have what the VO2 max is. So everything on the top is going to be positive relationship. As training volume goes up, VO2 max also goes up. The bottom ones are all negative relationships. So as weekly training volume increases, VO2 max decreases. So you can see in this first one here, there's not really any clear line or relationship between these data points. They're kind of random plot dots everywhere. And so you get a very shallow slope showing that there's not really much relationship there. As these correlation values increase, you see these data start to form more of a shape, creating a line. And so here, the steeper that line gets, so the more consistent those dots are across the line, the stronger the relationship. Same thing's true for the negative values. As these data get more clustered into a line, that's where you start to have a stronger relationship. Now, something I want to clarify, correlation does not imply causation, so it's not clear how these variables are related. And an example here is just because if you increase your weekly volume, that doesn't necessarily mean you're going to increase your VO2 max. This is just a snapshot showing that those with a higher training volume have a higher VO2 max. Okay, so an example of this, there's a study that looked at the number of concussions among teams that wore helmets that had animal logos compared to teams that had helmets that did not have animal logos on it. And it found that there was a relationship where there were fewer concussions if they had an animal logo on their helmet. Now, does the logo have any influence on if someone sustains a concussion or not? No. So this is just that's one example of why correlation does not mean causation. So one variable does not result in a change in the other variable. It just tells us, hey, there seems to be some relation going on between them. Okay, the last slide we have here, this just gives you a little flow chart of what you can use to determine which test is most appropriate. If you have a one group, you're going to be using either a one sample, paired, repeated measures ANOVA, or correlation. If you have two groups, you'll be performing a paired t-test. And then if you have three or more groups, you'll be performing an ANOVA. So I know statistical tests can be a little challenging. We're going to spend more time in class exploring these and identifying the appropriate time to use them, as well as actually taking a look at some code to how to actually perform these analyses. If you have any questions, write them down, bring them to class, or post them on the discussion board, and we'll play around with this more when we meet next.